I want to start with this Gilbert cartoon. Scott Adams is not my favorite, to be honest, but you know, this cartoon is pretty good. So the pointy-haired guy says, "I've hired a consultant to help us evolve our products to use blockchain technology." The little dog says, "Blockchain, blockchain, blockchain." And then the pointy-haired guy says, "It's as if you're a technologist and philosopher all in one." And then the dog says, "Blockchains, sidechains." So this is kind of, I think, how a lot of us feel. There is this word, blockchain, and you know, what does it really mean? What is it supposed to represent? We're going to get pretty concrete in this class. I'm going to describe to you how certain things actually work, and also try to put in context, you know, what I think is interesting and novel about the technology. And hopefully, you know, it's not the case that just because there's something novel about technology, it's useful, but at least with that, you know what's actually new and what existed before. So you kind of have a sense of what is the delta here? What are we playing with? What's actually happening? So the word blockchain, I think, is an umbrella for a lot of different types of ideas. The term was never defined until the Bitcoin white paper came out. Satoshi Nakamoto, when referring to the term blockchain, put a space between block and chain. I don't know who was the first person to remove that space. But a lot of the technology actually predates Bitcoin by decades. So technology like digital signatures, hash-based append-only logs, distributed databases. These are things we've, you know, known how to do for quite a while. And post-Bitcoin, a whole bunch of other interesting ideas in cryptography have, and finance, have sort of also gotten mixed up with this word. So cryptocurrency, smart contracts, zero-knowledge proofs, also very old technology, tokenized assets. And like I said, some of these technologies are from the 70s and the 80s. So I think when people use the word blockchain, they're often referring to a bunch of different technologies, and it's important to really get in there and figure out exactly what they're trying to say. So if someone says, "I'm doing blockchain for identity," you know, that's not enough information. You gotta really get in there and sort of try to figure out exactly what it is that they're trying to do. We're gonna go over a bunch of different concepts, but I wanted to show you, this is the Genesis block in Bitcoin. So this is where it all started. This is a block. It is, in this case, not a set of transactions, but it's an encoded, it's encoded data, and it's the first block of the Bitcoin blockchain. Satoshi Nakamoto released it either January 3rd or 4th in 2009. Now there is a little bit of human readable text inside this first block. What this text says is, "Chancellor on brink of second bailout for banks." So I want to pose this question to you. Why do you think that Satoshi decided to put that text in the Genesis block? Yeah?
One, to timestamp it, and also to say, you know, this is kind of the ethos of why I'm doing this. Like, sort of the reason behind.
Yeah, so I think there are two reasons. One was definitely to make a political statement, but the other was to timestamp it. Do you want to explain how this timestamps it?
It couldn't have been earlier than the 3rd of January of 2009, because you wouldn't have known the headline of the newspaper. Sure.
So that's a fair point. This headline was not published until this newspaper was put out January 3rd of 2009. You know, arguably Satoshi couldn't have predicted what the headline, exactly what the headline was going to be on January 3rd of 2009. But how does this prove anything? Does anyone know, like, why does this prove something? What does that mean? So this gets into, you know, what the blockchain is and how it works. So this data in the Genesis block, we compute a function over this data called a hash. And I'll explain to you what a hash function is in very high level terms. But what this does is this creates a kind of a fingerprint of the data. The rest of the Bitcoin blockchain all ultimately refers back to this fingerprint. If you tried to change anything in this text later, so for example, if Satoshi tried to sneak the headline in at a later date, it would have effects all the way down the blockchain. It would completely change the data and the fingerprint of the rest of the blockchain. And so by encoding this piece of data in here, Satoshi, and building the blockchain the way that the blockchain is built, Satoshi has sort of fixed in time what this Genesis block could be, has proven that, you know, he or she or they didn't create it before this date, and also because of the way the blockchain's built, because of the way hashes work, has also ended up proving that it's still the same as what it was before. So we're going to go into a little bit more about this. Okay, so what is a blockchain? The way that I like to describe it is in three pieces. So you have network software. You have nodes in a network, usually computers, that are all running a computer program and that are speaking a network protocol with each other. This protocol that they're running is producing an append-only log of data. So each computer in the network might add to this log, and each computer in the network is going to store a copy of this log. And using some of the cryptographic techniques we'll get into, it's going to be constructed in such a way that once something has been added to the log, you can't really go back and edit it. It isn't feasible to think about computationally going back and editing it. So network software running a computer program, in the case of Bitcoin, it's the Bitcoin software, which is located on GitHub. You can download and run it yourself. And these nodes are speaking this protocol and all adding to this log. Now, the part that people don't talk about as much is how you use this log. So what you do is you can think of this log. This log could contain many things. In the case of Bitcoin, it contains transactions, payments, a payment from one person to another. But it could have lots of different kinds of records. It could have operations that are happening on data. If everyone has the same log and they run the same program over the same log, then they'll all end up with the same database, the same state. In the case of cryptocurrencies like Bitcoin and Ethereum, this state that they produce is who has what money, or in Ethereum, what's the state of all the smart contracts in the system. So network software producing an append-only log, the same append-only log, and when everyone runs through that log, they get to the same state of who owns what money in the system. This is secured via cryptography. We use digital signatures for users to indicate consent to transfer. We use hashes for tamper resistance and integrity, and we use consensus for agreement. And I'm going to talk about all three of these things. But I want to pause. Any questions so far before we get into it? Okay. So let's start with what put the crypto in cryptocurrency, which is cryptography. So what is cryptography? Cryptography is a field of mathematics, and it's the study of how to secure information, how to make sure that things that you want to keep secret can be kept secret. Also, how to verify the integrity of some data. So how you know that a piece of data is authentic or that it hasn't been tampered with, and more. Now, behind the scenes, you are using cryptography all the time. You're using it every single time you get on the internet. Every single time you use your credit card or you download an app from the App Store, you are employing cryptography. Your browser is a pretty sophisticated crypto system, actually. So when you're actually using these things, there's usually one of two different things happening. Sometimes information that is being sent over the internet is being encrypted. That's the case with when you type your credit card number into a form online. But sometimes you're using cryptography to check and make sure that data is authentic. So for example, when you download an app on your smartphone from the App Store, the Apple App Store or Google Play Store, Apple and Google put what are called digital signatures on those applications to show that they officially approved this binary, this application. They vouch for it. And your phone will actually check this digital signature and make sure that it's valid whenever it downloads a new app. And this can help prevent you from downloading malware. Okay, so digital signatures. Digital signatures basically have the same purpose as traditional handwritten signatures, hence the name. That's why they're called digital signatures. So let's think about why handwritten signatures are actually useful. You use your signature to endorse something, for example, a check, right? It's proof of your identity. So a person's signature needs to have certain properties. It needs to be impossible to fake and impossible for the signer to deny, ideally. And then also the second property is that it needs to be easy for anyone to check. Okay, these are the two properties that we are going for with digital signatures. So when you sign a check, a blank check, the idea behind that handwritten signature was that it would have these properties, that whoever was looking at the check could have some sense that this was a unique signature that only you could provide, and they could check that quickly. So what are the differences between handwritten and digital signatures? Well, unlike handwritten signatures, digital signatures are produced with your computer. So handwritten signatures, you take a pen, you put it on paper, anybody can write one pretty quickly. Digital signatures are a little bit more complicated. So, you know, you might be wondering, how can a computer generate a signature that can't be faked by anyone else? And how does the signature actually tie to my identity? How does this all actually work? Well, it's interesting. Everyone can actually use the same program to generate a digital signature. We all sort of use the same algorithm when we're computing them, but we each have some kind of secret that we're using to produce our digital signature. So no two people should have the same secret. And what the guarantee is behind digital signatures is that if someone doesn't know your secret, then it's almost impossible for them to produce a signature. So handwritten signatures look like this. Digital signatures might look something like this. You know, remember, there was an important property of signatures. They're supposed to be easy for anyone to check. How are you going to check this? Unfortunately, you also have to use a computer program to check a digital signature. It's usually the case that you can't just really eyeball one and check and see if it's valid. So there's another computer program. The first one that produces it is usually called Sign. The second one is called Verify. So there's another type of computer program. Again, everybody can use the same program, but with different inputs for different signatures that will take the signature, take your input, and tell you whether, and take a message and tell you whether or not this is a valid signature on that message. Importantly, this verify function only uses public data. You don't need to know any secrets in order to validate someone else's signature. It's an important property. So you might be wondering, okay, great. So you produce this kind of gobbledygook looking text thing, and that's supposed to mean that I signed something, but how are you really supposed to know that? What actually ties my identity to my password, to my signature? So how can a computer actually check that I signed something? Well, we don't actually use identities. So the way that these systems operate is that you can kind of generate as many identities as you want. Identities are just pseudo-random numbers. They look like random numbers, anyone can generate as many of them as they want. I could generate 1 million very quickly and have 1 million different identities that I can use to sign things. Usually what ends up happening is that there is another system, it's called a PKI, for public key infrastructure, that helps map these random numbers to human readable, meaningful things. An example of a PKI is the certificate authority system. Every time your browser loads a website and you see that little green lock up in the corner, it's using a PKI to validate signatures and to enforce that you're really visiting the website you think you're visiting. So if you go to, for example, Fidelity.com, you're going to see that little green thing. And what's happened is that Fidelity has paid a third-party company that specializes in this to vouch for the fact that this is their special random number. That special random number belongs to the company Fidelity. Okay, so digital signatures, a little trickier than handwritten signatures, unfortunately. Great. So, question, are digital signatures really secure? You know, if I see your signature, then can't I just copy and paste it digitally? That's super easy. Well, digital signatures are actually much more secure than handwritten signatures, and the reason for that is digital signatures depend on what message you're signing. So yes, you can copy a digital signature, but it's only a valid signature for the message you already decided to sign. You can't copy a digital signature from one message onto a totally different message and have it validate. So this is a really nice property. Okay. So quick vocabulary lesson. I already mentioned the term public key. Usually in the signature schemes that we use today, we use public key cryptography. So public key cryptography, also called asymmetric cryptography, the idea behind it is that there's two parts. A public identifier, a public key that is your kind of your identity, the random number that you're going to map to your identity. So it's a little bit like an email address. And then a private key, which is mathematically connected to this public key. And it's the secret information that you're going to use to be able to sign something. So it's a little bit like a password, except you never actually type it into any forms or give it to anyone. It's a secret that just lives on your computer and that the program you run to sign things will suck up, read, and use to sign things. So public key, public identifier that that sort of signifies who you are. You can give this to as many people as you want. Private key, please don't ever give this to anyone. You should never share this. And it is the secret that enables you to both unlock things that might be encrypted to you and also sign messages to prove that they came from you so that anyone can verify that they came from your public key. Okay, and to be clear, both of these just look like really long random sequences. Now, you might be wondering, why am I telling you about all of this? Public keys play, well, public-private key cryptography plays a pretty important role in blockchain technology. These are the identities that we're dealing with in blockchains, public keys. They constitute Bitcoin addresses, Ethereum addresses. You use your private key to control your coins. So when you say that someone has cryptocurrency, it's not that they actually have, you know, coins sitting somewhere. They have private keys that can control those coins. So, so public-private key cryptography. Okay, great. Okay. So next cryptographic primitive we're going to talk about is a hash. So also very important in blockchains. So there's a function, a cryptographic hash function, which has certain properties. It takes some input and it produces some output, okay? And a hash, so we use the word hash to refer to both the function, like I'm going to hash, actually use in three ways, to refer to the person. Yeah, this is all about. Refer to the person, hash, sitting right there. We use it as the function, I'm going to hash this data, and we also use it to refer to the output. This is a hash, okay? So three different things, verb, noun, person. And the hash, the thing you get out is kind of like a fingerprint corresponding to that piece of data. Fingerprint's not exactly the right analogy, but I think it's useful. So any piece of information, any piece of data, a string, a sequence of bytes, an image, a PDF, an email, a video, anything, you can make a hash. You can hash it. You can produce a hash from it. Everything has a hash. And an important property of hashes is that different pieces of information have different hashes, okay? So the hash can almost act like a unique identifier for perhaps a much bigger piece of data. So I could take a report that I wrote in high school, shove it through a hash function and get a fingerprint at the end that is pretty short, 32 bytes, and perfectly sort of represents the entirety of my very long report, okay? It's a way of condensing something down into a unique identifier. Okay. Now, just to be clear, you might be wondering, is it possible for two different things to have the same hash? Yes, it is possible for two very different things to have the same hash. However, it's very, very, very unlikely. So in practice, hashes aren't actually fingerprints. They're, again, random sequences of bytes. So it's going to look like some large random sequence of numbers and letters. Now, the key idea here behind hash functions, the thing that we really want out of them, is that it's really hard to reverse them, okay? So given, say, a picture, and you produce a hash, it's really, really, really hard to figure out, to just take that hash and figure out what picture came from it. Now, if you have a sequence of pictures, if you have 5 pictures, you can try hashing them all and seeing which one matches that hash. You can totally do that. But if all you have is the hash, you can't derive the picture backwards from it. In fact, the best way usually to figure out what picture corresponded to that hash is to try all of them, like all the pictures in the world. Okay? So this is a really weird, neat feature of hash functions. It's very easy to go one way. Super easy to just shove some data into a hash function. You can do it on your computer, but very, very hard to go the other way. Given a hash, very hard to figure out to find the specific thing that generated that hash. Okay. In fact, like I said, the best way to do it seems to be, for good hash functions, to just keep trying data at random until you get lucky. And that could take a really long time. Okay. So putting this together, a blockchain is a chain of blocks. What does that mean? Well, a block is a sequence of records. So each of these is a block, sequence of records. In the case of a cryptocurrency like Bitcoin, those records are transactions. There are people paying a person or the other. And what do we mean by a chain? Well, each block has something very special in it. It has a hash of the block that came before it. Okay? And this is a way of sort of time-stamping, fingerprinting, securing the data in the blockchain. Because so to be clear, the hash here is not for this block, it's the one that came before it. This hash is for this block, and this hash is for this block. And that includes the little hash that's also in there. So you form this chain of hashes in the blockchain. And the reason that we say that it's tamper-proof, you might have actually heard that blockchains are immutable. I don't like to use that word. I prefer tamper-proof. But the idea is supposed to be that if given a blockchain, given someone, an inspector, who's watching the blockchain, who's looking at the end of it and is keeping track of what the hashes are, if you want to go back in time and fiddle with a record that has already been sort of committed to the blockchain, then what that's going to do is that's going to have a trickle-down effect. So what's going to happen? If let's say that we're in this situation, and I try to go back in time and show someone a blockchain, just that record changed. What's going to happen? Yeah.
The hash is going to change with that block, and so it's not going to match the next block.
Exactly. So because I changed a record, the hash is going to change for this block. That's going to change that hash, and that's going to change that hash. And so whoever's watching the end, can see all of this happen. And remember, it is very, very. So one thing we could try to do is we could try to change this in such a way that it keeps this hash the same. That is incredibly hard. That's what all of the security tamper-proof resistance of blockchains rely upon, is the fact that it's very hard to do this. So just to be clear, if you hear something like, oh, there's been a break in SHA-2, you should be very worried. Bitcoin's over. Okay, good. All right, great. One thing I do also want to add is that, cryptography is great and it protects us from this happening. However, we're still basing security on certain assumptions, where we have an assumption that it's really hard for someone doesn't have enough hash power to go back and try lots of different things and compute a different blockchain. You could just randomly brute force that. We haven't sort of protected against creating multiple versions of a blockchain and showing different versions to different people. The reason that we say that blockchains are tamper-proof, you can't go back and edit the past, is because we're assuming certain things about the way the network works that will maintain these properties. Sometimes these assumptions get violated, and I'm not really going to talk too much about what happens, but given that we're in a class where we're discussing ethics, I think it's important to note that all of these systems come with honesty assumptions, or assumptions about what kinds of powers different adversaries have. And if those assumptions are violated, you don't get the properties that you were hoping to get out of the blockchain. Okay, so blockchains were originally developed to solve a problem called the double spend problem. We know how to make digital tokens. It's pretty straightforward. David Chow in, I think, the late 70s came up with an idea called eCash, and even started a whole company around it called DigiCash. And it was a way of creating these scarce digital tokens. The part that David Chaum didn't figure out was how to create these digital tokens without a trusted third party in the middle. And so now I'm going to explain to you how to do that. And the reason that you need a trusted third party, or what I'm about to describe to you, is because we will have to solve the double spend problem. A digital token can very easily be copied. We want to make sure that if I pay you one digital token, you want to be pretty sure that I haven't paid that same digital token to 3 other people, right? You want to know that you're the only one who has that digital token and I haven't just multiplied it times 4, because money doesn't really work that way. You're not supposed to be able to costlessly copy money. So in order to solve this problem of making sure that there was only one blockchain where we could enforce that each coin had only been spent once, we're going to use a concept called distributed consensus. So what is distributed consensus? What is consensus? Consensus is actually a pretty old problem in computer science. It predates Bitcoin by decades. It was described in the 1980s. And the main idea behind distributed consensus is we want to make a distributed system with many possibly failing nodes look like one computer. Okay? So we're going to have a lot of different computers that are all talking to each other over a network. They all start with different initial values. Some start with red, some start with blue. Some of them might fail, they might go away, and we still want, as long as enough of them don't fail, we want to be able to reach agreement, such that any of the computers that didn't fail will all agree that the decided upon value was, in this case, it's blue. Now, something that's very cool is that even if some of these computers are evil, even if they're malicious and they are actively trying to subvert agreement, as long as enough of them are honest and are online, we can still reach consensus. This is pretty cool. This is what's called Byzantine fault-tolerant consensus. So it's a fault tolerance model, and it's based on an idea by Leslie Lamport. He described in the 80s a problem, the Byzantine generals problem. Leslie Lamport really liked to make up stories about his algorithms and his protocols. So the story with the Byzantine generals problem is as follows. You can imagine that there's a city which is surrounded by an army, and that army is controlled by many different generals. The generals all need to attack the city at the same time in order to defeat it. Well, enough of them need to attack at the same time in order to defeat it. And if they don't have enough attacking at the same time, they will all lose and their army will be slaughtered. So they all need to agree upon whether a time that they're going to attack, okay, at the same time. Now, problem, the generals can only communicate via messenger. So messengers are running back and forth between these armies, and messengers can be killed. And there are some traitorous generals who are on the side of the city and who are trying to actively subvert their agreement. So that's kind of the setup for the problem that he's describing. It's called the Byzantine generals problem. You might hear sometimes that Bitcoin solves the Byzantine generals problem. That's not true. In the very same paper where Leslie Lamport formulated the Byzantine generals problem, he provided a solution for the Byzantine generals problem, so I don't know why people say that. It's very strange. But it doesn't solve the problem, so to speak. But it is, I think, a useful way for thinking about what the problem is. Okay. So here's a little bit of the history behind consensus. So 82, we have Leslie Lamport's paper. We have several different algorithms written protocols that solve different versions of the consensus problem. And in fact, there was one developed right here at MIT in 1999 that didn't really get a lot of use after it was created, but now is being employed in tons of blockchain projects. So it's very interesting to see that 20 years later, this protocol is being kind of dredged back up and people are using it in the wild. 2009 is when Satoshi Nakamoto introduced Bitcoin, and Bitcoin doesn't exactly work the way that traditional consensus protocols work. It works in a quite different way, and we call that Nakamoto consensus. So when you hear Nakamoto consensus, we're talking about the way that Bitcoin works, which is called proof of work. There's been development since Bitcoin, so it's not just proof of work. And people are now talking about proof of stake. And there's a lot of different algorithms that are being used. This proof of stake is relatively newer. Bitcoin's been around for 10 years. It's been running in the wild for 10 years, pretty successfully, and it has almost a $200 billion market cap. I would say it's pretty well tested. Some of these proof of stake protocols are not, they haven't been around as long, they're not quite as well tested. So the left side, so pre-Bitcoin, we have a lot of protocols that are all sort of based on voting. The idea behind these protocols is that the nodes are known and they're all going to vote on what they think the next value should be. Bitcoin is a little bit different. It's not a protocol based on voting. It's based on hash functions and incentives. Okay, so before I get into this, I wanna pause there and sort of find out if there's anything else anyone wants to talk about with consensus. Yes.
In his paper, how did he solve the Byzantine generals?
We're gonna get to that. Yes.
It's not solved, right? It's just probabilistically less probable that.
You can think of it as solved. I mean, Leslie Lamport, how did Leslie Lamport solve it, or Satoshi Nakamoto?
Yeah.
Oh, there's a protocol. There's a protocol for voting, and as long as fewer than 1/3 of the generals are bad, as long you can tolerate up to 1/3 of them being bad, then you can run this protocol, which collects a whole bunch of votes, and then you can have some confidence that everyone's going to agree on the same value as you. It's a voting-based protocol.
Do people argue that Nakamoto consensus solves it because it allows 50%?
Yeah, no, not exactly. I don't know why people say that Bitcoin's the first to solve it. I think Bitcoin is the first that solved it in a setting where we didn't know who we were dealing with. Let me put it that way. Okay.
Kind of like permission and permission.
Yes, exactly.
Yeah.
Yes. Yes.
Leslie Lambert's story is the original Paxos paper is hilarious.
Yes. Yes, it is.
Written not as a distributed algorithm, but as a fictitious archaeological.
Yes, I will link to it. And Leslie has said he ultimately regrets writing it that way because it delayed people being able to understand it for like 15 years because everyone was like, what is this? You're writing this thing about the price of olives in Parliament, and you know, I'm a computer scientist, what is this about, right? So he won the Turing Award eventually, so he's fine. Okay, great. Yeah, so we'll link to those papers too in case you're interested. The Paxos paper is kind of interesting to read. Okay, great. So the key thing here is before Bitcoin, we knew who all the actors were in the system. And all of those protocols on the left side of Bitcoin, Paxos and PPFT and all of the ones that Leslie Lamport developed, all sort of assumed that you knew the set of nodes or computers with which you were trying to reach agreement. Now, the thing with Bitcoin, I think that's so fascinating and so interesting and really different is that we don't know who we're dealing with. We don't know who the nodes are. We don't know what their public keys are. And we're still able to, amidst this sort of anonymous set of participants, reach agreement. Yes?
Kind of in terms of permissionless blockchains and what you said about bad actors, like how can you identify in the system who is a bad actor? Or I'm guessing that does that mean a bad actor means like they're trying to change something in the system?
Yeah.
And how would you identify that actually?
Good question. So one of the features of blockchains, which I'm just going to go back to the picture, this is a bad idea. Okay, this is okay, hold on. It's too late now. I've moved it. This picture, right? All of these nodes in the network that are running this computer program are running a computer program that is checking every entry that is added to this log and making sure that it conforms to certain rules. Mm-hmm. And if it doesn't,
the mathematical rules, right?
Yes. Yeah. Are hashes valid? Are digital signatures valid? Are they the right size? All sorts of things. There's a set of rules. And if at any point it sees a block that contains something that violates one of these rules, it will ignore it, and it will ignore the entire chain it's in. So that's something also that's a little bit different here, is that I'm actually going to be running the software myself. I'm going to be running software that will check at every step of the way that the chain that I'm looking at is following these rules. So you ignore bad actors is part of the answer, but it's not the whole answer. But I don't know that we're going to get to the whole answer. And in 2009 or 2008, the really key idea here is Nakamoto consensus, and it's a way of reaching agreement that is not based on these identity protocols. It's based on something called proof of work, and it has spawned an industry called mining. It's called mining because as we are reaching consensus and producing new blocks, we're also producing new Bitcoin. And so it's kind of like you're mining for Bitcoin. So this is a picture of a data center it contains this specialized hardware that has been designed to do this process very, 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 very fast, okay? So tons of these machines, this is probably in China, that are churning away, computing random numbers and securing the Bitcoin blockchain. So let's talk a little bit about how that works. So like I said, in the previous set of protocols, participation was based on identity. You knew who you were dealing with in the system, you knew who the set of voters were. Now the problem if you don't know who the set of voters is that a malicious adversary could execute something called a Sybil attack. They could create a whole bunch of new identities and flood out the honest participants. Because participation is based on identity, because we're using voting protocols here, this is kind of a disaster. You have too many adversarial votes. So the key innovation behind Bitcoin and Nakamoto consensus was to make identities cost something. So it wasn't the case that an adversary couldn't generate new identities. They could definitely generate new identities, but they had to pay a lot of money in order to do it. And the security assumption behind Bitcoin is that adversaries will just, instead of trying to sort of spend their money subverting the system, will instead spend their money being a part of the system. So in addition to the fact that identities are costly, there is a crypto-economic sort of feedback loop here where we have an incentive system. The producers of new blocks are actually rewarded in new Bitcoin and in transaction fees. And so there's this whole sort of very delicate balance that appears to be working so far, where people invest in giant data centers like that in order to compute this, this cryptographic puzzle and to continue securing the Bitcoin blockchain. And in return for that, they are rewarded with new Bitcoin, which is worth something. So I have a lot more to go, but I'm just going to talk about one topic quickly, and then maybe we'll switch over. And perhaps we'll find some time in the next class to go into some of the details about how transactions work and things like smart contracts. And this is sort of the basis of blockchains. This is what they're based on, but there are a lot of sort of layers and things that I think would be helpful to know. But the one thing I do want to quickly get into is this idea of decentralization. This is a word that's thrown around a lot, and to be clear, I think that I don't think there's a very good definition of it. So the best that I'm going to do right now is give you an intuition rather than a formal definition. So a decentralized system is one where no single organization is in control or is a single point of failure. And I'm going to amend that to be single or small number. So, you know, the image on the left, if this central node disappears, you know, the system doesn't work anymore. The nodes are no longer connected. You can think of an application like Instagram, for example. If Facebook disappears, boom, there goes Instagram. You might still have the app installed on your phone, but I can pretty much guarantee you it's not going to work if Facebook servers suddenly disappear. We are dependent on Facebook for the application. In a decentralized system, ideally, an entire organization or set of people could disappear, and the network can kind of still heal itself. It can still keep operating. This is what systems like Bitcoin, to some extent the internet, were designed to do. Okay, now we are not going to go into transactions because we are running out of time, and hopefully we'll find some more time to talk specifically about sort of what's happening on top of the blockchain. Any questions so far about any of that? Yes?
I have a question about the decentralization part.
Yeah.
I imagine that, like, in the larger Bitcoin graph, it's not a fully connected graph. In general, how is it determined how a node that's entering the network chooses the peers it connects to?
Great question. I can tell you exactly how that happens. So if you were to start up a Bitcoin node on your laptop right now, I think the software comes hard-coded with a specific DNS address. It will go ask, so it's sort of like a website. It'll go ask that DNS address for to resolve, and it'll give it a list of what are called seeds. It'll give it a set of starting nodes to connect to. So it's kind of hard-coded in some ways. There are people who run different DNS seeds, and they can change the specific computers that are behind those DNS seeds. But there's a set. I don't know exactly how many there are, but not a huge number. So first, your computer will connect to those nodes. Then, through a gossip mechanism, it'll find out about other nodes, and it will connect to other nodes in the network. You can also, if you have a specific friend or peer that you want to connect with, you can tell your node to connect to that peer directly.
Okay.
Any other questions? Thought I saw a hand. No? Oh,
sorry,
yeah.
it just like we're talking about decentralization and like lack of centralized authorities.
No, this is a fair point.
It seems like an example
Yes.
of a centralized
No,
authority,
this is
but
great.
it sounds like there's the flexibility for me to just ask
Exactly.
what his next
Exactly. So I think you're absolutely right, and people talk about all this all the time. Who
Okay.
controls the DNS seeds for Bitcoin? They're the ones that any new node will connect to. But it sort of feels like even if those were all supposed to go bad, we could, or if those were all to go bad, we could get around it pretty easily.
Okay.
So I think that's kind of the type of system that we're dealing with. Yes, there is a specific set of addresses that are sort of tentatively hard-coded into Bitcoin. Number one, those are not all controlled by the same group of people. They're controlled by many different people. And we're dealing with a system, a peer-to-peer system. You just kind of need to talk to at least one honest guy. As long as you can get yourself in there, as long as you're not totally eclipsed, then you can become a part of the network. So I would argue that it's not as bad as Instagram, Facebook, for example. But you're right. There's sort of levels of decentralization and of control.
Thank you, Neha, for that introduction to all of the cryptography that underlies these systems and to the into distributed systems as a concept. And so now what we're going to do is we're going to, for the next 35 or so minutes, we're going to do a little kind of like moderated debate kind of, where we have Neha, and then we also have James Mickens. And James is a computer science professor who just got tenure. Congratulations.
Oh, congrats. I didn't know that.
And James has a good skeptical perspective towards blockchain and cryptocurrency technology. And
It's a terrible way of putting it. I appreciate that.
Nice, yeah, exactly. So we're going to do a little bit of a battle here between Neha and James. I'll ask a good amount of questions. Feel free to come in with other questions over time. We'll have a little time at the end also to ask questions. So, and the goal here, I think, is to give us kind of a, just like Neha's talk, give us more of a technical understanding, but also some of this skeptical understanding as you all approach your projects and the rest of the semester. What are the kinds of skepticisms that you should have in your mind? Like, how can you embody James? And how can you also push back against that? Because the skepticism might be legitimate, but also might be illegitimate. So, with that much said, I just want to, I guess, ask you, James, from the start, what do you think most either beginners or experts misunderstand most about the technology and how it can be used?
I think they misunderstand the guarantees that blockchains can provide. And I think that at a high level, blockchains are very attractive because they have a lot of interesting buzzwords like decentralized, secure, tamper resistant, things like that. But I think that in particular, when you look at the permissionless system, you end up seeing that, at least in my opinion, most of the use cases that people would want to have a secure, tamper-resistant, scalable ledger, the properties people want are not actually the properties that they might get from something like Bitcoin or Ethereum, right? And so, as an example, think about any type of system that uses mining, proof of work, for example. If you look at Bitcoin right now, roughly 75% of the mining power is in China. That's neither good nor bad. That is a geopolitical truth, though. So what does that mean? That means, let's say you're some business owner, you want to put stuff in the Bitcoin blockchain, right? Are you comfortable with 75% of the mining power living in a regime where, if the central government gets upset, they lean on those miners, they can cause forks or things like that. So I think it's really important if you're thinking, I want a blockchain for reasons X, Y, and Z, to consult with someone who is deeply technical and see if the blockchain actually provides X, Y, and Z. Right? The last comment I'll make is that it's very similar to if I got in trouble with the law, right? I would not represent myself in court because I'd be going to jail, right? Because I don't know how the law works at a deep level. But I think that blockchain is very seductive in that it allows people who are not sort of necessarily deeply technical and understand how the code works to make technical sounding claims. So like lawyers will say, oh, smart contracts are like laws. There is a big semantic gulf there. Be careful about that. Economists will say, oh, cryptocurrencies are like fiat currencies in many ways. There's a very big semantic gulf there. Be careful. So that's why I think that the threat model, the properties that the blockchain provides, that's why they're so misunderstood.
And that makes Neha, do you agree with that?
100%. Yeah, no, I agree with most of that, except for the mining thing. But that's like a bit of a rabbit hole we could go down. But no, everything else, 100%. You know, try to. There's a huge amount of hype, and we started with that. And never forget all the hype. We have to be careful about what claims we're making, for sure.
Do you think, and I guess this is essentially back to the question that we were dealing with at the end, which was at the beginning with Bitcoin, when you look at seeding nodes, you have to ask yourself, what are the trust, people use the terms, correct me if I'm wrong, what are the trust assumptions that you have? Who are you trusting in the system or not trusting? What are your security assumptions in the system? And then what are some of the attack vectors? Like how can the system be attacked? Are there other words like that that I'm...
I think the main one is threat model.
Threat model, that's
sort of the word used to describe a lot of that. Yeah, what's your threat model?
And that takes into account all those assumptions.
Yeah.
Okay. So another question I want to ask was, there's that good piece of reading before class today about the 5 different camps of crypto.
I was going to get to that. It's at the end, though. Sorry.
It's okay. It's okay. And the 5 camps, to remind you all, are there's like the Bitcoin sound money camp, which is kind of what Neha was explaining, people who are super into this censorship-resistant money. Then there's the internet payments camp. Those are people who want to make a new kind of money on the internet that you can give and receive money super quickly over the internet. You don't have to have, instead of going through Visa because they have too high transaction fees or whatever. And then there's the Web3 camp, which is like Ethereum and other smart contracts. So you have these new smart contract platforms that can send and receive money programmatically over the internet. And then there's Camp 4, which is instead of on the smart contract layer, kind of on the application layer, it's what people call DeFi, or decentralized finance, or open finance. And that's people who are messing around with these smart contracts and kind of making new weird kinds of derivatives and like financial instruments. And then there's Camp 5, which is the distributed ledger technology camp, which is kind of the enterprise blockchain camp, and people who are interested in permission systems. So, of those camps, I guess for either of you, which camps are you most like, yeah, that's a sweet camp, or which camps are like, ooh, I don't like that camp? What are you skeptical or not skeptical of for each camp?
Well, I think the camps are use cases, right? The camps are, what might this be useful for? Might it be useful for recreating derivatives in this very, without a trusted third party? Or might it be useful for digital credentials that are used to log into social networks in your phone and things like that? I don't think we've gotten far enough to tell what it'll be useful for. I do think it appears that some people are finding it useful as a store of value, kind of censorship-resistant money, non-government money thing. I don't think that's the most exciting use case, but that's the one I think that's been proven out so far, at least on a small scale. The other ones are still, we're still working on.
Yeah, so I was just looking at the definitions in that article, which are very good. That's a very good article for understanding sort of the lay of the land. I basically hate all these camps for different reasons. So, like, the thing with the sound money camp is that the thing is a lot of people who are very excited about cryptocurrencies have very little understanding of how economics works. We've been through this whole sound money thing with the gold standard. Didn't work out too well, right? Like, you can actually look at actual economics research to see what happens when you have the type of sound money that a lot of people in this camp argue for. It does not end well. So this is kind of similar to what I was saying, like a lot of people who like blockchains because they think like smart contract of law, they are not lawyers. They don't understand some of the implications of this. I think that for the payments camp, I agree in theory that it's useful to be able to reduce, like, let's say transaction overheads. That seems perfectly reasonable, right? But blockchains, but that doesn't necessarily mean that blockchain is the right solution for that, right? Like, why does Visa take such a huge cut of things right now? It's not because blockchains weren't invented, it's because competition was low and barriers to entry were high, right? So the mere fact that those two economic conditions hold does not then necessitate that blockchains are the right technical solution. And I would argue they are not, for reasons we can discuss later.
Well, for example, the swipe fees in Europe are tiny fraction of what they are in the United States, so they're propped up here by legislation.
That's right. We have existence proofs for the fact that you don't need, blockchains to reduce financial transaction fees. For the open finance camp, I mean, perhaps many of us might agree that, like, let me not make assumptions. I would claim financial engineering is largely worthless. Why is that? Because the whole point of financial engineering should be to enable new types of businesses to exist, right? Loans, options, futures contracts, all seem great. But what do we see throughout the past 50 years? Things like collateralized debt obligations caused a housing crisis. They're mechanisms for obfuscating risk, right? So I don't think that I've seen anything that's like super compelling in that camp. The Web3 camp, I like ideologically, because ideologically I would like for, let's say, me to have a social network that's not just controlled by Zuckerberg and whatever island he's bought up. There will be challenges there with actually performance and scalability and providing features. And we can drill down on that later if people are interested in that. But like, roughly speaking, we went through one phase of peer-to-peer excitement back when Napster and stuff like that came out. And I think the lesson of a lot of that interest was that if you want to get the same types of features you have with centralized applications, it becomes more difficult. For example, to do like large-scale machine learning in a fully decentralized way. And then the decentralized ledger technology camp, this is like enterprise blockchain. These are just people who are just branding. So like, there's been a lot of work in the distributed systems literature about how you make highly scalable storage systems, right? So if you look at Hyperledger, which is an enterprise blockchain, like it ends up not looking very much like, let's say, Bitcoin or Ethereum. Things which I think are actually intellectually interesting for the reasons that you mentioned, because they say, hey, how can we create identity in a world where we don't have strong identity roots? But like, that's certainly not the case in the enterprise situation, right? Where you need to be able to sue people and say, you are who you are. So I don't think there's a lot of innovation necessarily that like blockchain specifically bring to that. I now see you talking stick.
Yeah, so this is the problem. I mostly agree with James, but I still want to work on this stuff. I will just say there is one little sort of thing that I will get at, that I will poke at a little bit, which is to say that we have not really had multi-organizational databases in the past. People have not you haven't had the case where you had different organizations, different companies, different countries, different whatever, all running the same logical database. And I think with I'm just gonna go work backwards from all the stuff you said. So with things like Hyperledger, I agree, they are not that intellectually interesting from a technology standpoint, but maybe all of this hype and these buzzwords are actually causing consortia of companies to come together and to figure out how to run a logical data store all at once. And it's not using any of the new technology, it's using the stuff from the 80s, but that's perfectly fine. Because unfortunately, the economies and the society and products don't always keep up with the edge of technology. Sometimes we find uses for old things whose time has come, and perhaps it was in fact this new blockchain stuff that inspired them to think about that. And part of the reason that so I've been very negative on permission blockchains most of the time until I actually talked to some economists who thought that there might be some benefit to cooperation and in the incentives between these companies to work together. And so I think we really need to see how that plays out. It's not clear to me that I think 99% of what's out there is hype, but there might be a kernel of something. Moving forward, I totally 100% agree with James on the fact that decentralized systems almost always perform worse than centralized systems. And so it's going to be very difficult to recreate a lot of the social networking and sort of like rich, beautiful applications we're used to in this environment. In addition to that, decentralized systems are really hard to upgrade. They're really hard to coordinate. So you're not going to be able to move as fast. You're not going to be able to implement new features as quickly. So all sorts of things that are going to make it hard, I think, to do that. So but there's one thing that they've got going for them that I think is actually quite different, and it is embodied in things like Bitcoin, which is the fact that it's outside of the existing system and existing regulation. There are certain things you just can't do right now. I can't write an application that takes micropayments. I just can't. There's no libraries out there. Visa won't do it for me. Stripe won't do it for me. There's just no way, right? And part of there isn't exactly a technology reason for that. It's as a result of the sort of the competitive landscape that has come up. It's a result of the way the banking works and the way that Visa works and the way that all the companies work and the payment systems in the United States. And yes, Europe is an existence proof that it doesn't have to be that way, but we don't have that here. And so these systems, I think, coming sort of up outside the existing regulatory landscape and the existing competitive landscape can at least act as a forcing function and potentially maybe in some cases even an option that is not being provided in these other cases.
Yeah, so I think that's helpful, and I think that understanding, when you put on the skeptical hat, one part of the skeptical hat is understanding this classic thing that James is saying, like, oh, how much are you doing armchair economics or armchair lawyerness and bringing that into the computer science world? And then, as you're both saying, it's like scaling these systems, like decentralized systems are very hard from a variety of technical perspectives. And I think, though, that on the positive side, I think that Neha's hitting on a really important point here, which is, especially as we think about blockchain ethics, is that these are not just purely technical systems, that this like existence proof of payments being better in Europe is a sign they are socio-technical systems, and that there are incentives at play that are outside the system, or norms or laws or things like that that are part of this. So I want to ask a question to James about, like, do you like, you hated on each of those 5 camps to some extent. If you could you create a 6th camp that you would love the most, or is there like something that you would, what would that 6th camp look like?
Well, I think Neha hit on a really important thing that I really believe in, and that to the extent that I think that blockchains have been helpful, it's been to make, let's say, for example, enterprises realize like distributed databases are a thing.
Yeah.
Like, you can do that. And like, I've also talked to economists and like, business people too, who just say like, that in and of itself is useful. Like, for example, it is useful for a company that used to be like pen and paper, or like, metaphorically speaking, sort of Stone Age, and they say, oh my goodness, like using this blockchain, I can do X, Y, and Z. Now I would say, don't worry about the blockchain part, but the fact that they have now sort of like awoken, they say, oh my goodness, well, we could create a consortium. We could exchange data in some standardized format, right? So like, I think that, to me, like, that's what's so interesting about it. I think that there is also something very interesting, once again, getting back to this notion of identities, and how can we get anything accomplished if there are no centralized roots of trust? Now, I think that it is interesting that Bitcoin and systems like Ethereum have seen, that they figured out this interesting way to make forward progress there, which, depending on what metaphor you want to use, it's like, identities as CPU cycles or things like that. That's interesting. Now, I would claim that in most business-to-business, consumer-to-consumer, enterprise-to-enterprise scenarios, that's not actually a reasonable assumption to have, but it is interesting to think about. So to the extent that it's made people realize that distributed systems, and really technology in general, can help to solve some of these problems that traditionally were pen and paper, accountants do it, or like very inefficient, I like that aspect.
Yeah, okay, so it sounds like that 6th camp would be something that is really just getting people woke to the things that not necessarily like permissionless blockchains solve, but rather these new ideas about distributed databases and identities. Yeah. Okay, so I think one thing also for folks to be aware of is that when you're trying to understand these systems, there's often, and Neha mentioned this earlier in her talk, where she doesn't like the term immutability. You prefer the term like tamper-proof.
Tamper-resistant.
Oh, sorry, exactly. Thank you, exactly, because I was about to say that a thing that people in the blockchain and cryptocurrency world do often is create these binaries, or these like 100% truths, where they say like trustless or permissionless, and or immutable, or tamper-proof. And so I guess I wanted to just get your take on any of those. I have a list here, the permissionless, trustless, immutability. Which ones are you the most skeptical of, or are there any that you're like, oh, this is actually a truth, like this is 100% true all the time? Any of those binaries?
I mean, I'm filled with hate, so I don't want to. I don't want to filibuster. It's like that Fidel Castro over here.
Yeah.
So, I mean, for example, right? Eyes roll in the back of my head, right? So think about the decentralized aspect of it, right? It's very interesting to think about what decentralization means in a situation where identities are anonymous, right? Because if you think about it, like when you talk to like most economists, game theorists, or whatever, fairness is oftentimes defined with respect to being able to say particular identities can or cannot do certain things, or cannot acquire certain things. But so like if you have systems that are anonymous, it's actually hard to enforce notions of decentralization that would resonate with most lay people. So for example, like think about Bitcoin, right? Like in a certain sense, it's very liberating to say, one CPU cycle, one vote, zoinks. But if CPU cycles have a relationship with power in the fiat world, then if you're very rich in the fiat world, you can get very many CPU cycles and you can mine more than like your proverbial, you know, mom and pop miner. That's interesting because that means then that power in the mining sense tends to accumulate as fiat power tends to accumulate. And what is accumulation? It means centralization, not decentralization, right? And you see this in the way that mining pools work, for example. You see this in a variety of other aspects. So to me, the one thing that I find very subtle about some of these anonymous or pseudo-anonymous systems is that they say that, in a certain sense, they want you to believe that because they are peer-to-peer, because there is no centralized admission authority, these systems will therefore tend to go towards a steady state of there not actually being centralization in practice. And I believe that is false, right? And this is another thing that I think that people see when they look more at the economics of a thing, right? It's all fun and games to be anti-regulation until you start seeing this accumulate. Look what happened to Burning Man. Right, Burning Man used to be like this libertarian paradise, and then what happened? Now people are flying in like, you know, air-conditioned Zeppelins, right? Why is that? Because there are no checks and balances against accumulation. So for me, the decentralized part plus the anonymous part, that's where I see personally the most tension.
Yes, so I think this is really interesting, actually, and I do think that when we look at the systems we have so far, they do display these properties because I don't think they were designed very thoughtfully. And to me, it's an open question. Is there a way, can we possibly design these systems with the appropriate sort of checks and balances or regulations or tensions or forces that will keep them from sort of following this path? You know, if you look at cryptocurrency holdings, for example, they're pretty highly concentrated. We're much worse than the existing fiat world. If you look at things like, you know, my point about mining power is that it's not really actually that great of a power. You don't have as much control as one might sort of say you do. But if you look at sort of, you know, how that's aggregated, again, also very concentrated. And so, you know, I think it's really this open question: can we design a system that does operate in this peer-to-peer decentralized manner, but build it with the right parameters or tweak it in the right way so it doesn't naturally have this consolidation? I think that would be very, very interesting to do.
Yeah, I think that note for folks, I think a lot of the topics in this class will map relatively well onto early internet kinds of things, because at the early internet times, people were building these permissionless, pseudo-permissionless protocols. And when you have those protocols and people are like, oh great, we're going to have like 1,000 flowers blooming, and that is what happened at the beginning because it lowered the friction for these things. But then over time what you get is these massive Google, Amazon, Facebook aggregators, and this idea of aggregation theory is just that, yeah, if you decrease the friction for getting more suppliers and more customers, more of these things on your platform, then essentially certain platforms like Google or Facebook can win, or Amazon can win by creating a great user experience, and then everything just flows to them in a permissionless kind of way.
Yeah, if I could add, oh, sorry.
Why is that a bad thing?
Why is that a bad thing?
So I think it's a bad thing when it affects user choice. I think it's a bad thing when we as a society decide that we don't like what these entities are doing with their power.
If you have the perfect thing that is on the market, why does it matter if you do not have a choice? Why do you want something more inferior?
Well, so, like I said, I think it's a problem when we don't like the actions that these entities are taking, and we don't have a way to give that feedback or to make that choice to sort of indicate that. If we don't like, for example, you know, Facebook, I think doesn't let you post pictures of mothers breastfeeding. It's just they will take it down. The market is porn. It's not allowed, right? There were some women who, as a protest, were posting lots of pictures of themselves breastfeeding. One of them got basically locked out of her Facebook account. No more Facebook for you. And it was really interesting to see the effects that actually had on her life. She couldn't log into Tinder anymore. She couldn't date. She couldn't log into Spotify. She couldn't comment on the New York Times articles. So you see, this action that this control that Facebook has, this power that Facebook has, actually was quite significant and affected a lot of parts of her life. And I don't think we really intended Mark Zuckerberg to be able to say who is allowed and not allowed to comment on the New York Times. You know, that wasn't a power that we really wanted to give him, right? We didn't want him to be able to say who can date and who can't date. And unfortunately, the way that we've built these systems is that we've unintentionally given this amount of power to these entities, and they're showing us that they're, quite frankly, not using it very well.
But I would say, though, just really quickly, that, I mean, some people will see that as sort of like, not necessarily a feature, but certainly not a bug. I mean, there's some people who, ideologically speaking, say, this is the price. So, for example, like, you know, you look at the volatility of, let's say, Bitcoin. Some people say, ideologically, I would prefer volatility versus having a Federal Reserve. Yeah. You know? And so, like, that's actually another interesting opinion to think about, because, like, the true hardcore ideological people right? Regardless of whether you think that they're good or bad, they would not be uncomfortable with this scenario because they would say like accumulation is just sort of like that is what the hand of Zeus wanted.
But I would say, I don't want to argue this side because I'm not on that side per se, but I do think open access is incredibly important. And what we've seen is we started with this suite of protocols that were quite open access. I could run a server, you could run a server, we could get IP addresses, we could talk to each other, I could put up some data, and Reese could get to it, right? There weren't gatekeepers. We could all run our own websites, and there was a little bit of gatekeeping at the country level jurisdictional, but for the most part, it was pretty open, and we could say whatever we wanted to. Unfortunately, we moved from HTTP and that layer to apps on our phones that are gated by app stores. So I can't get my app onto your phone unless Apple or Google says that it's okay and blesses it. So we've moved from anybody can put up a website to Apple has to say that your app is okay. And by the way, they exercise this judgment. I have a friend who his app didn't get approved because it was too avant-garde. What does that mean? I don't know, but he's not allowed, and it's not the case that it's impossible to install the app on your phone if you're so motivated. You can do things like root your phone or say, I allow it to not install from the official app store. Yes, I promise it's okay. Nope, I know what I'm doing. I promise. Yep, I'm not gonna sue you if I get a virus. But it's really, really hard. Like you've essentially cut off access by creating this gate, right? And so I want to move things to a place where there's a little bit less gatekeeping by companies that we didn't elect into office, that we don't really have the means to regulate yet.
Alex, were you going to have a question?
It was related to a previous point.
That's okay.
Oh, go for it.
Yeah.
I thought what you were touching on before, bringing it back to like the economics portion of this, is these big companies as monopolies, where part of the harm that a monopoly does to a capitalist society is the barrier of entry is very high, and then it restricts our choice, and also means that they can make choices because the barrier of entry is so high. And it seems like in the US at least, we have this like ethical connection to capitalism. Anyhow, do you see a way of constructing a decentralized cryptocurrency network or other decentralized network that would be monopoly resistant?
I have no idea how to do that. I think that would be very cool, but I don't know how to do that.
I think it will, yes, I agree with that. I think it's actually going to be very hard to do in practice because as far as I can tell, when I talk to like both computer scientists and economists and people like this, there's this tension that we were talking about before between like decentralization and anonymity. Mm-hmm. I think if you're willing to, in a certain sense, compromise perhaps in some of the anonymity, mm-hmm. or compromise perhaps in having regulations for some issues of regulation, to sort of say like, here's how fairness is defined with respect to particular principles, then maybe one could start thinking more about fairness. Just as a concrete example, consider a permissioned blockchain, right? Which maybe technically are perhaps not as interesting as permissionless ones. But what's interesting about the fact that like in a consortium of companies that are in a permissioned blockchain, every company knows who the other companies are, is that now you can actually think about like punishment and reward and incentives and disincentives in a very strong way that you can't necessarily do when you're in a system where nobody knows who anyone else is, and you're sort of making these vague high-level assumptions like most nodes are honest, for example. So to me at least, that's the key challenge there. If you're willing to allow from some type of identity that is sort of can be the target of enforcement penalties or rewards, that's one thing. But if you're not willing to go down that route, I think it becomes much more difficult, for example, in the permissionless setting.
If I understood your last question correctly, you were asking about the use of language, right? So there's and imprecision, I think, was the word you used, right? So there's this imprecise language, and then the experts, the nerds here in the room, are capable of speaking more precisely, right? And I didn't hear you answer that particular question. Would you mind addressing that question? Or if you did, could you make it clearer? Maybe I was just too stupid to understand the answer.
For a specific example here, why, when people say blockchains are immutable, why is that actually not true? Or is it fully true?
I don't understand the meta question.
like why the difference, why the gulf between sort of like the buzzwordiness and sort of the actual technology, like why that's a problem?
Is it why? Yeah, is it why we care about that, or is it why does it exist?
Okay, so where I'm coming from is that just before that, the question just before that was about how we might be able to get people excited, for example, in the corporate world, by using words that they get excited about, but are actually not correct, right? And so here, the issue is not in precision, but it's deliberately using wrong terms for productive purposes, right? So that when you drive down towards precision, you're actually losing the. You're nodding, so I think I don't need to say more.
Yeah, I mean, part of this is just like the way that like product gets sold. And I think that part of it too is that, you know, whenever you have any field, there will be experts in that field. In a certain sense, gatekeepers, who you have to trust to a certain extent to give you the metaphor level explanation, but then for internally, they actually know the real thing, right? So I don't think that in and of itself is a problem. So for example, like, you know, with the law or with medicine or anything like that, with finance, you know, when you go to a doctor, the doctor, when they tell you what's going on with you, they don't necessarily speak in terms of like a medical textbook would use, right? But you trust them to know at the lower level what's going on. That type of semantic gap is perfectly fine, right? And so, but I think that the problem, I think that we both agree on, or all three of us agree on, is that there are some people for whom they don't understand what that gap really means. And they're then talking to other people who also don't understand what that gap means. And that's where you can get sold snake oil, right? At least that's what I see the problem as, right? So I see like salespeople come in and say, blockchain everything. It's immutable, which means that nothing can be deleted and stuff like that.
You can get sold snake oil, but you can also be convinced that it's a good idea to use this wonderful blockchain, which isn't actually very new, in parentheses, but you get excited about it by it. So there's the snake oil, but there's also the positive aspect.
Yeah, actually, your question is making me really think a lot about how we communicate across different disciplines, because so I've spent a not insignificant amount of my time trying to explain what this technology is to people who are not computer scientists, and you know, I felt a moral imperative to try to be as accurate as possible, while at the same time not hiding behind. Is pedantry a word? But hiding behind sort of, you know, a very precise vocabulary that isn't really meaningful to them, quite frankly, and doesn't need to be meaningful to them. It's sort of, you know, engineers have a tendency to sort of nitpick everything, and oftentimes those little differences when you get to a high enough level aren't actually really that important, quite frankly. So it's really interesting to think about. Are we trying to pretend like we're wizards by using some of this language, right? I think there's a lot of that in the blockchain space too, where people use very complicated language to try to appear really very smart and very intelligent, and instead of sort of breaking things down in a very simple way and thinking about, well, okay, what's lost, what nuance is lost when you break things down in a simple way. But then again, what are you trying to do exactly? When I'm talking to a regulator, do they need to understand whether or not Bitcoin has synchronous or asynchronous or semi-synchronous network assumptions? Probably not, right? I mean, what do they need to understand? And that's me making that judgment, trying to explain it. And I don't know, your question just made me think of more questions, but I think it's very interesting.
So let's do one question, and then we'll start to get into wrap mode. Yeah.
So there's a lot of discussion here about trust and reallocation of trust, and I'm curious where you see the primary places of necessary trust in these blockchain technologies and how that reinterprets and reconsolidates power. For example, I can verify some of the proofs that blockchain is true. I cannot verify any of the system myself, and I find it very hard to understand whether the models involved are actually well applicable to the real world.
So that's a great question. I think even if you can verify the proofs, are the proofs saying the right thing? Are they? Is the model reflecting reality? Who knows? So yeah, there's a lot of trust assumptions that you are making. You are trusting that the software that you are running is doing what you think it's doing. You're trusting the software developers who wrote that software. you know, operating system, your CPU, your network, your ISP. You know, it's kind of crazy when you think about all the different levels of trust that are involved. I don't really know that I have an intelligent answer to this other than to say, yeah, there's a lot of things that you are actually, in actuality, trusting. But I will say that I think the developers, the good cryptocurrency developers that I've met, are some of the most paranoid people I've ever met in my entire life, and are trying to think of, perhaps not in a principled way, but they are trying to think of all the possible ways that things could go wrong, and that, you know, their MacBook could subvert the software that they are running, and they do think about all of these things, and they try, again, in somewhat of an ad hoc way to address them.
Yeah, I mean, I think that, like, everything that we do sort of, like, is built upon, like, you know, turtles upon turtles of, like, different trust assumptions. Right? Even just, you know, can we even trust the hardware? Right? We've seen like all these hardware bugs recently. It's like, oh God, if we can't trust the hardware, what hope do we have of the software being correct? I mean, I think for me, the key thing is that, you know, a lot of the problems that we see in the blockchain world, I mean, the problems that we see in like other aspects of life. You know, like if you want to get a mortgage and then you get some like 20-page document, like what does that actually mean, capital M, right? And so, you know, I think that like, what I at least find interesting about the blockchain was something that I sort of mentioned earlier, which is that for various reasons, blockchain technology in particular inspires people who are not necessarily technically qualified to make certain claims to make those claims. In part because the claims that they're making are attractive. They oftentimes deal with things that we want as individuals, like decentralization, like immutability, things like that. And so, like in a certain sense, all of these problems with credibility are issues that we have in other examples too, like, you know, how do I trust that I got the right bill from my healthcare provider, things like that. So I would just say do due diligence. Like my last comment, so I used to work at Microsoft before I went over to Harvard, and one thing that impressed me about Microsoft is that even high-level technical VPs, people who came up through the tech divisions, they have something called a TA, a technical assistant. It's like Satya, who came up through Azure, has a technical assistant. Bill Belowski, who used to be my intern mentor there, was Satya's technical assistant. What's the purpose of this assistant? It's when that VP comes into a room with a bunch of other people, the technical assistant can call BS and can say, hey Satya, yeah, even though you used to, you know, sort of make your money actually writing server code, you know, I'm your technical assistant. I will make sure that no one pulls the wool over your eyes. And I think that you should have that type of assistant for whatever you do. If you're doing a business transaction, right? Go work with a banker or someone like that you trust. So just make sure that the things that you understand at the high level are actually being reflected in the low level. And so I think that like if people did more of that with blockchain tech, I would be more positive about the technology first of all. And second of all, it'd be easier to figure out, here are the killer use cases. Here are the things that we truly could not do in any other way because we've got these technical assistants who are helping us understand those.
I think there's an incentive problem there. The technical assistants are incentivized to you know, make blockchain technology sound more useful than it is, so that they continue to have a job.
But no, the TA is for like you as the person who might be about to use it. It's not for the blockchain people, right? So in other words, think of the technical assistant as being someone's like you go in, you talk to the Hyperledger people.
Well, that's what I'm saying. The Hyperledger people are incentivized to say, Hyperledger's awesome and the technology's awesome, right?
And the TA's purpose is to whisper in your ear, right? And say like, hey, like be a little bit skeptical.
Okay, maybe I got this wrong. If the TA is a blockchain, you know, expertise TA, then they have an incentive. Like if I'm a cryptographer and I'm your technical assistant, oh man, cryptography fixes everything. Yeah, let's go do things in the world with cryptography. Like I want to make sure that those are the questions that people are asking about.
I mean, yeah, that's right. So if you pick a bad TA, you're hosed. So like your TA should be the friend who's going to be like, those genes do make you look fat. That's how like Bill was to me, right? Like, he told me that one. Bill has some harsh wisdom right there. And he said, I told that to Satya every day. Right? Because I wanted Satya to know that like I will be the nicest mean person that you ever met, and that I will try to avoid you getting down these rabbit holes. Anyways,
well, with that, James has to leave, but thank you so much for coming. Computer in a quick second, but I want to pop a couple things off the stack there for folks. The first is when we're thinking about this language piece, the real thing for all of you to be aware of is just when you see some of this binary language that's being used, always just have like a trigger to be like, oh, I'm a little bit skeptical of that. If this thing is making a 0 or 1 claim, immutability, trustless, whatever, there's probably some assumptions baked into that. So that's one piece. The second piece I want to say is Alex's question about monopoly resistance. I think Oh, I mean, in general, I think that Neha and James are correct in saying that there is that these systems are there are all kinds of technical issues with scaling them and doing ML on these systems. But one interesting piece about blockchain and cryptocurrency systems is that if you imagine trying to get new people into networks, it's very hard to get new people into like a new social network because you have these existing social networks like Facebook that has 2 billion users. And that's because the only gain that I get from existing networks is by like the user experience of that network. But blockchain cryptocurrencies are able to create new networks, Bitcoin and Ethereum and all these other ones, by financially incentivizing people to join the networks early. So instead of me saying, ooh, I'm thinking about joining a new network, I only think about the UX benefits and none of my friends are in that network, so of course I'm not going to join. Instead you say, ooh, I'm thinking about joining this new network, and there's both UX benefits and like user experience benefits that are pretty low at the beginning, but the financial benefits are maybe higher at the beginning to join this network. So that's a theory that some people put out there for how you might create these new kinds of networks with financial incentives. And then the final point I was going to say was on this question of balance of power that Neha was getting at, and how you create these systems that balance all these different kinds of power. Part of the issue within cryptocurrency systems is that almost, to some extent, a lot of those incentives are built around kind of just like code-based incentives. So there isn't much like law checks and balances coming in or norms checks and balances coming in. A lot of people use this kind of mechanism design mindset where they think about the incentives of the system and try to design these optimal incentives such that when the code is produced live, it will create a beautiful new social network. And in fact, the world is more complex than that. We'll dive into that mechanism design perspective later in section 2, but that's just like a preview for how a lot of folks think about designing optimal systems purely from a code perspective. So, with that said, Neha, do you have anything else to add?
Yeah, I'm not sure what our timing is looking like, but we didn't really have a lot of time to discuss that. So I was thinking, the class might like to sort of talk about what we just did, but but I am sensitive to time. So
I think that we can. I think that we can discuss for 5 to 7 minutes. So,
and there might not be any discussion, but I think
let's open it up. Does anybody have any thoughts on what James or Neha said there?
I would really like to drill down further into that question that you, if possible. I thought that was a really good question. Can I try and rephrase it? So you were talking about reallocating trust, right? Or in a sense, it's also reallocating power, I guess, right? So for example, if Neha goes off and talks to regulators, they have to trust her to represent the issues, but she's actually becoming powerful in that context, right? So, and was that what you were getting at? So we're talking about some people losing power, some people gaining power. Was that the point of your question, or what?
Yes, that was half of the point of the question. That is something I wanted to investigate.
And what's the other half?
I guess one of them is just what are the main centers of trust that are necessary, and where is this actually being reallocated, rather? And the other is how does that relate to this redistribution and flow of power? Because those two things absolutely go hand in hand, but I don't think are necessarily the same.
Where did you guys end up after sort of the beginning of the debate? And so how many of you have came in here thinking blockchain technology was really cool and you wanted to build something with it in the first place? How many people were kind of interested in it? So I'm interested. We're all interested.
Well, interested and building, or interested?
Both.
Okay.
Either. And did this sort of conversation make you realize that maybe some of the things you were interested in are harder to build than you might have thought, or it might not be good, or did you realize other things that would be good for it? Yeah.
Well, I'm interested in places where the trust in the overall system of government or the controls that are there are probably worse than blockchain and Bitcoin is now. As bad as it is with local problems, I think there are a lot of places in the world where it's still better than the local government. So I think that's an interesting area.
Yeah, think something that I was thinking about is like I feel like it's almost like we didn't have the governance or like system design conversations soon enough. Just like in general, I feel like people have just been barreling ahead, which makes sense because like that's how you get to the moonshot. That's how you get to like the next iteration. So like just thinking about that. But then also thinking about like, okay, there's a lot of different use cases and sort of which use case is going to come first, and kind of prioritizing that. And I think I had my thoughts of what that could be, and like now, like even a year later, I'm like, oh, like maybe that's going to be different. And I think stuff around in like the financial system, like that stuff is going to be really slow. So is there going to be another use case outside of like the financial system that might help like prove this and then help like more people get on board? So those are just like some questions I was thinking about as you guys were talking, because I do think to his point, like there's a lot of people using blockchain, but where blockchain doesn't necessarily need to be the solution. And so how do we like think about noise and implementation costs versus like actual like full fidelity of the product and it being very useful. I was also part of a research project where we interviewed a bunch of companies 1 year, and then 1 year later we kind of went back to companies and we said, you know, like, was this harder than you expected to implement? Like, how far out are you still from implementing your projects?
All blockchain projects.
Mm-hmm. In different industries, and it was just really interesting to see is like a lot of them were like, it's much harder than we expected. Here are like the main obstacles we're still facing, but we're also more optimistic than ever in terms of implementing it because we actually feel like there is like XYZ use case. So like even in that I felt like sort of conflicting, but like this is like these are real people, real companies, and I can send around the link and stuff, but yeah, it was just really interesting. So just all of that was coming back as you guys were talking. I was like, yeah, like, you know, where do we all still stand on this?
Could we take that? She's offering to share.
Yeah,
I'm
we'll
going to
share
send it right now.
since
We
it
just
is
got
an
published
email
today,
link.
so yeah.
Nice, good timing. Hachihi, what were you gonna say?
Just my own small thoughts. Like, I feel like it seems like we are just putting too much burden on the, you know, the blockchain itself. Like, you know, for example, there's someone who wants to be, you know, is there a way that we can use blockchain to prevent monopolies? Is there a way that we can generate through blockchain? I mean, like, let's be frank. I don't think there's a system that can do any of that, right? It's like we are just placing too much emphasis on, you know, like what an ideal world can build on this blockchain. But I think we should just go back to the basics. You know, what's blockchain? A decentralized way Byzantine solver, I mean, kind of. And, you know, think about what can we do with it and what the implications of doing those things. I mean, like for example, James was talking about, you know, how blockchain or cryptocurrencies could, kind of subvert the financial system that we know now. And he spoke about the gold standard. Well, I mean, he said like the gold standard was a failure. It was a failure from the US point of view, but not from other people's point of view. I mean, stagflation only occurred in the US, not elsewhere in the world, right? So US was the one who came off the agreement, and then the US decided, hey, screw you guys, I'm just going to go back to my fiat currency. And I mean, that's one point of view, but what's the other point of view? Like, it created a stable currency, stable, not beneficial to the US sense, but beneficial to some other countries.
Yeah. I definitely want to agree that we should look at what the actual affordances are and what can be done with blockchain, but I'd like to push back a little on we shouldn't try to ask if like you can do mechanism design to ensure a monopolyless system or market. Partially because, frankly, a lot of cryptography does things that look impossible already. So
I mean, you're trying to solve a social problem with technology. I think that's the biggest problem. Like solving you're trying to tackle the core fundamental philosophical problem that we had for millennia, right?
Yes, but
where should power be concentrated? Should we have democracy or, you know, dictatorship?
a lot of those are caught up in coordination problems, and having a software system that you can agree upon on the beginning that, like, in very powerful ways enforces certain sorts of coordination could solve some of those problems.
But what's the fundamental problem is that we can't even agree on what we agree on.
Okay. I think that this is, this is exactly the things that we were talking about versus the technology. Can we do mechanism design to solve some of these problems? Or actually, you want to say one final and then we'll get into wrap mode?
Oh, okay. One of the things that James made me think more about when he was talking about permissionless versus permission blockchains was this tension between transparency and this concept of trustlessness. Like, I think that what partly made everyone really excited about, like, the original Bitcoin paper was this idea that you could have a system where people can have anonymity or pseudo-anonymity. Sorry,
it's a hard
tough
one.
And it could operate as a trustless system. But he was pointing out, well, one person with a lot of money and power could pretend to be all of these different nodes because they have enough money to spin up that many nodes, and without transparency, you don't know whether that's going to be the case. And it just made me re-question whether you can truly have this trustless system where people can be anonymous.
Yeah, I thought that was a really interesting tension that he brought up that I had not deeply thought about before. Okay, so we have 5 minutes left, so I want to get into full wrap mode. Let me plug in my computer here. Thank you for the conversation. And I guess as a note, by the way, and I'll talk about this in a second, but there are, we will have on Monday from 6 to 9 p.m. when we have our kind of recitation period. That's the perfect time to kind of go deeper on some of these topics, and I think it's likely that this week we will, to some extent, go deeper on this upcoming Monday. That will mainly it'll be a time to talk about the things that we talked about in today's class. I think we'll probably go a little bit deeper on smart contracts in Monday's recitation period, and then also start to talk about the readings for next week. So that's really all that this is a quick preview of what we're going to talk about next week. We're going to talk about the tech ethics side of, and as a reminder, let me put this up, that there you can view blockchain ethics from either the lens of tech ethics or money ethics or institutional ethics. And next week we're going to talk about the tech ethics side, which is mainly viewing the affordances of the technology from a technical perspective, where you say, okay, you have the centralized ledger, now you have the distributed ledger. How should that make us think about privacy versus security? How should that make us think about anonymity and those kinds of things? Or if you see the blockchain cryptocurrency as this new layer of the internet protocol stack, a new permissionless, unstoppable code protocol that is decentralized and kind of disintermediates trusted institutions, then there are some questions that brings up, like, well, how can we make sure we have humans in the loop? Or how can we have coherence given the decentralization that we're pushing for? So these are the same things that all this stuff happened with the internet as well, and so we'll essentially map it onto this world.